Edward's been associated with CMI a lot longer than I have. He's been a friend of CMI since its inception. He was on, I did just check this with him, he was on the inaugural scientific board. He was involved in selecting the Millennium Prize problems. And we all know what a profound influence Edward's ideas have had on both mathematics and physics. So in the tradition of minimizing non-mathematical talk, I won't run through a subset of his many achievements and honors. Instead, I'd just like to thank him for being such an abiding friend of CMI and for agreeing to give a lecture today. And he's going to talk to us about gauge theory and the analytic approach to geometric Langlands. Thank you.
So I'm going to be explaining work with Davide Gaiotto, mostly this paper, but this one is background, in which we try to explain in quantum field theory terms a new twist on geometric Langlands developed by Eddington, Frankel, and Kazan, but based in part on earlier work by Langlands and also on the physics side by Jörg Teschner, among others. So roughly speaking, in the first half of the talk, I'm going to, first of all, this new twist of geometric Langlands is more concrete in the sense that one studies quantum states and operators on quantum states rather than categories and functors acting on categories. But as I'll explain, in the quantum field theory picture, it can be described by the same ingredients organized in a slightly different fashion. So the first half of my talk will be a review of the traditional geometric Langlands as interpreted in gauge theory. And then in the second half of the talk, I'll actually explain the picture developed in these papers. So in the gauge theory approach, the starting point for geometric Langlands is a variant of gauge theory that's very widely studied by physicists. It's the maximally supersymmetric, or in the jargon n=4, Super-Yang-Mills theory in 4 dimensions, with the gauge group G, or with the Langlands Gardner-Olive dual group G dual. So either way, the theory has what's called a gauge coupling constant, E, and it has a theta angle, topological angle theta, dual to instanton number, and they combine nicely to a complex parameter in the upper half plane. Then the theory has an elementary symmetry that shifts tau by 1, which just says that instanton number is an integer, so the conjugate parameter theta is an angle. And likewise, the dual theory has a dual parameter, also with an elementary symmetry. The interesting thing, the highly non-trivial statement, is that the theories based on the gauge group G and its dual group G dual are equivalent under an operation that inverts the parameter tau. Now, mathematicians are widely familiar with classical gauge theory, but quantum gauge theory is really the province of physicists until now, unfortunately. Quantum gauge theory reduces to classical gauge theory if E is very small and therefore tau is near I infinity. The fact that this duality inverts tau means that it's impossible for both tau and tau dual to be near I infinity. And therefore, we're never in the regime where we can study both theories classically. That's why, well, first of all, it's why the duality isn't visible classically and therefore is an interesting quantum duality, but it's also why it's difficult to understand. And it took a long decades. The original conjecture was made in 1977. It took roughly 2 decades before physicists learned to effectively understand this duality and develop confidence that it was correct. Now, the statement made on this page isn't especially a statement about geometric Langlands. And in studying it, physicists are usually asking questions that have nothing in particular to do with geometric Langlands. But we can specialize to the situation that leads to geometric Langlands. First, we consider a topological twist that leads to a family of topological field theories parameterized by CP1, which I'll parameterize the CP1 by affine coordinates psi or psi dual. If we study the whole family, we find that we get these trivial equivalences that shift psi or psi dual by an integer, but we also get a quantum equivalence, similar to the one we had in the untwisted theory. The whole family becomes the dualities studied by mathematicians working in what's called quantum geometric Langlands. But for today, we'll just consider the basic geometric Langlands duality between psi equals 0 for G and psi dual equals infinity for G dual. By the way, I want to stress that the basic picture is completely symmetrical between G and G dual. In conventional formulations of Langlands, there's no such symmetry. And from this point of view, the reason there isn't is that we asked a question that was asymmetrical. The duality statements treated psi and psi dual symmetrically, but we decided to set psi to 0 and psi dual to infinity in order to get the conventional geometric Langlands duality. And at that point, we broke the symmetry between the group and the dual group. And therefore, we proceed to make statements that treat them asymmetrically. Now, in general, quantum field theory in dimension D associates a number to a D manifold called the partition function or transition amplitude or whatever, depending on the precise context. A vector space, the space of physical states, to a D-1 manifold, usually envisioned as an initial value surface on which initial data are formulated. So in the previous talk, we had initial data for the Navier-Stokes equations. Now we have initial data to which we associate a quantum state or a vector in a space of physical states. And then a category, the category of boundary conditions to a D-2 manifold. In the present context, although the theory is in 4 dimensions, we're going to specialize to 4 manifolds of the type sigma times C, where C is the 2 manifold studied in geometric Langlands, and sigma is some other 2 manifold. We will keep C fixed, but we'll vary sigma. Since we keep C fixed, we effectively will have a 2-dimensional topological field theory that depends on C as a kind of parameter. So we'll be doing 2-dimensional topological field theory, but it will depend on C. So then we define, in this case, in this situation, we define a category of boundary conditions that depends on C. Remember, in codimension 2, we define a category. Since C is kept fixed, codimension 2 means codimension 2 and sigma are just a point. So a point contains no information. What we have is just a category that this theory associates to C. Now I'm going to be drawing some 2-dimensional pictures in which I only exhibit sigma. So if sigma has a boundary, so it's a 2-dimensional picture, but there's a Riemann surface that's hidden, that's not drawn at all. What I've drawn here is a Riemann surface with boundary, the boundary shown by this black, solid black line. There might be other boundaries or something else somewhere else. I'm only drawing the picture near this boundary. If sigma has a boundary, then to formulate quantum field theory on sigma, we need a boundary condition. Or in other words, we need an object in the category. The reason boundary conditions make a category is that given 2 boundary conditions, B1 and B2, well, in a category, we should have Hom from B1 to B2, which will be a vector space. In this context, it's the vector space of physical states that quantum field theory assigns to this picture. In other words, if I'm given 2 boundary conditions, I can draw a strip with the boundaries labeled by B2 and B1. Sigma is understood as oriented, and the arrows keep track of that orientation restricted to induced orientations on the boundary. So in this picture, we could then have 1 manifold stretching between the 2 boundaries. And the space of physical states in that situation, we interpret as Hom from B1 to B2 in this category. So with this definition, for example, Hom from B to B is an algebra for every B. If I have a sort of a pair of pants, again, times a Riemann surface C that's not drawn, labeling all boundaries by B, we would sort of have 2 elements of Hom from B to B coming in and 1 going out. And so the quantum transition amplitude for that 2-dimensional surface will give us the multiplication in the category. And another picture I didn't draw will show that it's associative, although not necessarily commutative. And some more pictures also not drawn. Well, I could draw it. The picture that would show it's associative is this one, with 3 elements coming in. Well, we'd have to draw some more pictures to show that we could think of it as multiplication in 2 different orders. And some more pictures where some of the boundaries are labeled not by the same B, but by different B and B prime, will show us that Hom from B to B prime is a left module for Hom from B prime to B prime, and so on. So after a little while, we would discover that 2-dimensional topological field theory is more or less equivalent to having a category, the category of boundary conditions. And here we have a category, we started in 4 dimensions, so we have a category for every C. So, but also we have 2 different descriptions based on G and G dual. So electromagnetic duality will give us an isomorphism between the category curly C associated to C in the G theory at psi equals 0, and the dual category associated to C in the dual theory at psi equals infinity. Well, in addition, there's a natural mapping between certain natural functors on C and C dual. And these functors come from what physicists call line operators. So in general, in quantum field theory on a manifold M, a line operator is some sort of modification of the definition of the theory on an embedded one manifold K. So at psi equals infinity, the natural line operators, the simplest line operators, are what physicists know as Wilson operators. Wilson operator is simply the holonomy of a connection. We're doing gauge theory, so if we have one manifold, we can take the holonomy of the connection along that one manifold. That's a classical expression. Mathematicians will know it as a classical expression. In quantum field theory, such classical expressions become promoted to quantum mechanical operators. So then the holonomy interpreted quantum mechanically becomes an operator called the Wilson operator. The natural dual line operators at psi equals infinity are more sophisticated things that physicists know of as 't Hooft operators that turn out to be related to the geometric Hegge functors of geometric Langlands. Actually, last week at a conference in honor of Atiyah, I sort of explained this part of the story in more detail than I'll have time for today. Now, in physics, the Wilson and the 't Hooft operators are usually used in analyzing confinement of quarks in atomic nuclei and other subtleties about universality classes of quantum field theories. In fact, this would get us relatively close to one of the clay mining problems, although not quite. But, well, what I wrote is not quite, but 't Hooft was kind of thinking about the issues underlying the clay problem when he introduced the 't Hooft operators. For us, though, a line operator is a functor from the category of boundary conditions to itself. We can understand that statement from this picture. So here's a boundary of our picture. Here's a line operator, which could be supported on any one manifold, but I've chosen a one manifold that runs parallel to the boundary. And of course, there's a Riemann surface C not drawn. The boundary exists everywhere on C, but the line operator is localized at a point in C. That'll be important in a little while. Now, in A, the point is that a line operator running along a boundary with some boundary condition B just makes a new boundary condition TB. After all, we're doing topological field theory, so the distance between T and B is meaningless. We could bring T all the way up to the boundary, and whatever it is, we'll just get a new effective boundary condition that we'll call TB. So that explains how T acts on objects of the category, what it does to morphisms is shown in B. Well, the way I explained the composition law in the category before had to do with pictures like this. But, well, if we were doing a conformally invariant theory, well, we actually have diffeomorphisms, but even conformally, we could conformally map this kind of picture to this one, where a morphism just appears as a dot on the boundary, where the boundary condition possibly jumps or possibly not. But anyway, there's some modification of the boundary condition along a point on the boundary, possibly with a change in the boundary condition. That would be an element of, that's a picture representing an element of Hom from B to B prime, and then another dot Hom from B prime to B double prime. And the picture is meant to tell you that a morphism from B to B prime, if I compose it with T, will give a morphism from TB to TB prime, obeying whatever axioms you think it should obey. So I've been drawing pictures in 2 dimensions, but remember, there are 2 more dimensions not drawn, and T really depends on the choice of a point in C. Such pictures make it obvious that the line operators T of P and T of P prime, to begin with, for distinct points in C. So the picture represents acting on B with first T of P and then T of P prime. And in general, in such a 2-dimensional picture, T of P and T of P prime don't commute. If you multiply them in the opposite order, you'd get a different picture with the P line to the right of the P prime line. But we're really in 4 dimensions. And as long as the points P and P prime are distinct, we can move the 2 line operators through each other with no singularity, so they must commute. So the two dual categories, C and C dual, are equipped with dual families of functors parameterized by a point in C and some more data that I haven't stressed, and commuting at distinct points. So T of P corresponds to the usual Hecke functors in geometric Langlands, and W of P corresponds to its dual in the usual geometric Langlands duality, which is more elementary. And, well, I made various more statements in the rest of the slide, but maybe we don't have to go through quite that much detail. To go into a little more detail, I want to introduce a useful language for a slightly simplified version of geometric Langlands duality. So let M sub H of G and C be the moduli space of Higgs bundles of G on the Riemann surface C. So Hitchin showed it's a hyperkähler manifold. In one complex structure, it parameterizes Higgs bundles. In another complex structure, it parameterizes flat bundles with the structure group, which is the complexification G sub C of the compact gauge group G. And then these two complex structures are actually part of a hyperkähler structure, and there also are the corresponding hyperkähler forms. So a useful approximation to geometric Langlands duality is that it's mirror symmetry. So this Higgs bundle moduli space has a lot of different complex and symplectic structures. But in particular, you could take one of its symplectic structures, which was omega K in Hitchin's notation, and one of its complex structures, which Hitchin called J, and they're actually mirror to each other in the conventional sense of mirror symmetry between symplectic manifolds and complex manifolds. This instance of mirror symmetry, well, it has antecedents in the physics literature, but mathematically it was first studied by Housel and Thaddeus. So a good approximation to mirror symmetry, to geometric Langlands duality is this mirror symmetry. That was kind of, well, Atiyah had suggested back in the 70s that there should be some connection of Monton and Olive duality with with Langlands. He didn't phrase it in terms of geometric Langlands because geometric Langlands, as it's understood today, didn't exist yet. That was formulated by Bailenson and Drinfeld roughly around 1990. In other words, roughly a dozen years later. And because I was familiar with Atiyah's speculations, and also because it was obvious from the beginning that Bailenson and Drinfeld were using a lot of physical ingredients, for many years I wondered how the story could be connected to physics. But there were a lot of obstacles to understanding it in detail. So for many years I couldn't make any sense out of it. It was actually a lecture by Ben Zvi who did not say this, but who said something somewhat similar, which was phrased as a sort of asymptotic statement rather than an exact statement, at a conference here at the Institute, organized by Ed Frankel, especially, to try to educate physicists about geometric Langlands, that got me started in really understanding it. After Ben Zvi's lecture, I realized that a better approximation would be this statement, and that the really true statement was in 4 dimensions. And that eventually led to the story that I'm kind of trying to tell you about today, except that time doesn't really make it possible to explain it properly in one lecture. Anyway, an approximation is a mirror symmetry between two moduli spaces, but mathematicians working on geometric Langlands know well that completely correct statements aren't statements about finite dimensional moduli spaces. The conventional formulation is that you should have to work on the stack of G bundles, not on a finite dimensional moduli space. The physics counterpart of that statement is that you have to start in 4-dimensional gauge theory, not with a 2-dimensional sigma model. The two descriptions might sound different, but they're really the same because Atiyah and Bod explained back in 81 that a model of the stack of G bundles is the space of all connections on a fixed smooth G bundle, E over C. Unfortunately, here G is a complex Lie group, and here it's the underlying compact form. So 4-dimensional gauge theory can be viewed as a 2-dimensional theory with the target being Bun G. So when mathematicians somewhat abstractly talk about working on the stack of G bundles, for physicists, what that means concretely is that you should do 4-dimensional gauge theory, with the translation between the two statements being essentially what Atiyah and Bod said. Now, I want to use the two-dimensional description, though, to motivate the statement that the category on the automorphic side of the duality is a category of D modules on bun G. Well, so on the automorphic side, we've got an A model category, or a Fukaya category, of a real symplectic manifold Y, namely the Higgs bundle moduli space, viewed as a real symplectic manifold with the symplectic structure, the Hitchin code omega K. The most familiar branes of the A model are Lagrangian branes, supported on the Lagrangian submanifold L. But Kapustin and Orlov discovered that in general, you can also define coisotropic A branes that are supported on a coisotropic submanifold that's above the middle dimension. They discovered them because they needed them to make mirror symmetry work. They observed that in general, the traditional statement of mirror symmetry is not true if you try to use only Lagrangian branes, and they fixed it by including coisotropic branes. The construction of coisotropic branes is delicate in general and not very well understood, in fact. But the simplest case is the case that we need for geometric Langlands. That's the case that Y is actually a complex symplectic manifold with complex structure I and a holomorphic symplectic structure omega, and one is viewing it as a real symplectic manifold whose real symplectic form is M omega, the imaginary part. And moreover, you take the B field to be the real part of omega. That's one formulation. Kapustin and I actually phrased it a little differently. With that data, you can construct a canonical coisotropic A brane, BCC I'll call it, whose support is all of Y. So this is an extension of the Fukaya category as studied by mathematicians to include additional A branes that physicists consider to be necessary in the story, basically because otherwise, well, one thing is that you can define them. It turns out if you look for them, they have the same supersymmetric properties of conventional Lagrangian branes, but they were discovered because you need them for mirror symmetry. So it has extremely unusual and fascinating properties. Roughly, Hom from BCC to itself is related to deformation quantization of the algebra of holomorphic functions on Y. So, well, more specifically, well, this is perhaps not the most general statement, but one statement is that if Y is the cotangent bundle of some other complex manifold W, and the holomorphic symplectic structure of Y is the standard complex symplectic structure of the cotangent bundle, then you can show that this Hom space is the sheaf of holomorphic differential operators on W, twisted by K to 1 here. So in the case of geometric Langlands, we take Y to be the Higgs bundle moduli space. It's birational to a cotangent bundle, as was shown by Hitchin, where M of G is the moduli space of holomorphic G bundles on C. So the Hom space is the sheaf of holomorphic differential operators on the moduli space of bundles. And so therefore, if B is any other brane, for example, a Lagrangian brane, the more familiar branes in the Fukaya category, perhaps, then Hom from B to BCC is going to be a module for A, which is Hom from BCC to itself. So since A is the sheaf of differential operators, we learn that the category on the automorphic side of the duality will be, roughly speaking, a category of D modules on the ordinary moduli space. This was the interpretation by Kapustin and me of the statement formulation by Balancen and Drinfeld on the automorphic side. Now, mathematically, you have to work with D modules on the stacked bun G node or a finite dimensional moduli space. Physically, what that means is that this strange coisotropic brane, the one that extends the Fukaya category to include deformation quantization, can be defined directly in 4 dimensions, not only after reducing to 2 dimensions. Kapustin and I, well, frankly, we struggled with this. We had a version of it in our original paper that was correct but not very informative. Gallardo and I later found an improved version. And this improved version let us understand as physicists one of the important results of Balancen and Drinfeld. So the question is, what's the dual of this peculiar brane BCC itself? So BCC, the one related to differential operators, is an A brane of the Higgs bundle moduli space of G, so its dual will be a B brane of the dual moduli space. In other words, a coherent sheaf or a complex of coherent sheaves on the moduli space for the dual group. And Bailenson and Drinfeld, in a different language, had shown what the answer was. Its dual is what's called the structure sheaf of the variety of opers, a very special Lagrangian submanifold of the dual moduli space. I'll kind of give a definition later near the end of the talk. I won't pause to explain right now exactly what was the Bailenson-Drinfeld statement. But anyway, in the physics, it was important to understand why this was true. And we sort of got such an explanation a few years after the original work. So in summary, the main ideas in the gauge theory geometric Langlands correspondence, at least in the traditional form of the correspondence, which involves statements about categories and functors, as opposed to the analytic version, which will, in more recent developments, which will be the subject of the second half of my talk. The main ideas, as much as I can summarize them on one slide, are as follows. There's duality between the gauge group and the dual gauge group for supersymmetric gauge theory in 4 dimensions, twisting to make a dual pair of topological field theories, compactification to 2 dimensions on a Riemann surface C that you keep fixed in the rest of the discussion. The dual theories have dual sets of line operators, with the 't Hooft operators related to the geometric Hecke transformations, and dual Wilson operators associated to representations of the dual group. Then there's this, on the automorphic side, this distinguished brane BCC that establishes a map from A branes to B modules. On the other side, one is studying B branes on the complex structure in which Hitchin's moduli space parameterizes flat bundles with the structure group, the complex loop. So I apologize for zooming through that much too quickly, but it's as much as I can do to kind of summarize the traditional story. Now, however, there is one more point I want to make about the traditional story before I go on, because this will draw a contrast with the work of Ettinger, Frankel, and Kazan. The story so far involves deformation quantization, not quantization. And I want to take a moment to explain the difference very explicitly. And I'll take the concrete example of a two-sphere, x squared plus y squared plus z squared equals a constant j squared, viewed as a symplectic manifold with its usual rotation invariant symplectic form, which you can write this way, although that way to write it isn't manifestly rotation invariant. In deformation quantization, you start with the commutative algebra of functions on the two-sphere. And for example, you could consider polynomial functions and maybe complex valued polynomials. So this ring C of x, y, and z with this relation. And you want to deform this to a non-commutative algebra. And it's supposed to be an associative algebra. You specify that the leading non-commutative deformation should agree with the Poisson bracket. And you ask if there is a family of associative algebras over a power series ring C of h bar, or maybe formal power series, or maybe over a polynomial ring with this property. The difference is that in this case, you can set h bar to an actual numerical value like it has in the real world. And in this case, you have to think of h bar as a formal variable and work with formal power series, like perturbation theory in h bar, without being able to set it to an actual numerical value like 10 to the minus 27 erg seconds in the real world. So in this particular case, we can write down the answer. It's given by the SU2 Lie algebra. The associative algebra generated by x, y, and z with these relations, and essentially this relation, makes sense for any value of j squared. And well, the associative algebra with these relations makes sense and satisfies the conditions of deformation quantization. But that's not quantization. We haven't quantized the parameter j. It could be any real number or even any complex number in what I've said so far. Quantization means finding a Hilbert space H of the appropriate size that the algebra acts on. It doesn't exist for arbitrary j. To construct the Hilbert space, you have to quantize the parameter j, set it to preferred values at which the Hilbert space exists. And those special values correspond to the angular momenta in the real world. And it's because of this step that the subject is called quantization. So in the lecture so far, I told you that because of the Kapustin-Orlov coisotropic brane, the A model, or at least the extension of the Fukaya category in the right context, is related to deformation quantization, but not to actual quantization. But Gukov and I asked whether the A model in this general setup can describe quantization and not just deformation quantization. And the answer is yes, under certain conditions, which I have to explain because we need them for the application to geometric Langlands. Recall, in general, we're discussing, to get deformation quantization, we're discussing a complex symplectic manifold Y, viewed as a real symplectic manifold with the real symplectic form M omega. So now let's discuss Lagrangian A-branes. Well, these are A-branes supported on the submanifold L that's Lagrangian for M omega. In many examples important for geometric Langlands, L is actually a complex Lagrangian submanifold, that it's Lagrangian for omega, not just M omega. For example, if you take a skyscraper sheaf on the d-dual side, that means a sheaf supported on a point. Its dual is a Lagrangian brane, a complex Lagrangian brane, that's actually supported on a fiber of the Hitchin fibration. That happened because a point is hyperholomorphic. A point is holomorphic in every complex structure, which forces the dual to have special properties, which lead to it being Lagrangian for both the real and imaginary parts of omega. So it's actually a complex Lagrangian brane, Lagrangian for omega, not just for M omega. But in general, L need not be Lagrangian for omega, just as a coherent sheaf need not have any additional properties. Mathematicians studying geometric Langlands don't even mention the possibility that a sheaf could be hyperholomorphic. So it's certainly not a requirement. Agukov and I considered the opposite case of an A-brane B, whose support is Lagrangian for M omega, as is required in the A model, or for chi category, but is symplectic for real omega. And then we argued that in this situation, Ham from B to BCC represents a quantization of M with symplectic structure real omega. So that makes sense because we assumed that M is symplectic for real omega, so we can try to quantize it. And we claimed that the Ham space is then such a quantization. And so, for example, if Y is actually an affine variety, then you can show that holomorphic functions on Y, which were deformation quantized in the previous picture, act on this quantum Hilbert space with appropriate properties so that you can think of it as quantization of certain functions on M. So, sorry. This page really should have been a lecture, but you can't really do it. But I'll just have to make the assertion that so the previous case we had a complex Lagrangian brane, now we have the opposite case, symplectic for M omega, Lagrangian for M omega, symplectic for real omega. And then I claimed that in that particular situation, the A model knows about quantization, not just deformation quantization. I think that this probably should have interesting applications well outside of geometric Langlands. But anyway, for today, we'll head for geometric Langlands. So, well, there's an important detail. I defined the Ham space in general as a vector space with what Y is a Hilbert space. This page is devoted to explaining what we need to make it a Hilbert space, not just a vector space. And basically, we need M to be a real submanifold of Y. That means there's an anti-holomorphic map from Y to itself, with M as a component of its fixed point set. So, for example, at lunch, I was reminded that Nash proved that in 4 dimensions, every M is such a fixed point set of an anti-holomorphic involution of a complex manifold, even a complex algebraic variety. So we need M to have that structure. And the quantization, but the point is that if you're given M as a real manifold, its structure as a real algebraic variety isn't natural. You have to pick one. So here we have to pick one, and it should have some nice properties I don't really have time to explain, but Y roughly should have a good A model in the sense of physicists. Roughly, the A model of Y has to be defined over power series in H bar, not just formal power series. Sorry, polynomial functions in H bar, not just formal power series. So you can't start with any M and any complexification. It has to be nice in a sense I don't have time for. All I will really say is that the Higgs bundle moduli space is nice in the appropriate sense. So then given tau, there's a nice definition of the Hilbert space inner product using, well, universal properties plus this tau. So in this approach to quantization, if you're given a real symplectic manifold that you want to quantize, first you have to find a complexification of it to a complex symplectic manifold Y with some appropriate properties. And then you can use the A model of Y to quantize M. So that might be compared loosely to geometric quantization. In geometric quantization, you have to pick something, a polarization, roughly a maximal set of Poisson commuting variables, and then you get a recipe for quantization. So in either case, quantization is not completely natural. It can't be. There isn't a natural map from symplectic manifolds to quantizations. There's always some additional structure, either the complexification or the polarization. And either one can give good results if there's a natural choice, that's a choice that's natural for the problem at hand. Gukov and I didn't understand very much about how to compare the two approaches, but Gaiotto and I, motivated by the work of Edinger, Frankel, and Kazhdan, wanted to understand this better. We found criteria under which geometric quantization and quantization by branes will agree. So at the very beginning, I mentioned two papers, and one of them just was devoted to this point, really. We re-examined quantization by branes to understand better its relation to geometric quantization. Now, all this is by way of preparation to talk about the work of Edinger, Frankel, and Kazhdan that I mentioned at the start. So they considered a Hilbert space H of L2 functions or better half densities on the moduli space of stable homomorphic bundles on C. Then they construct operators on H that are related to the usual constructions of geometric Langlands and found interesting duality theorems and conjectures about the action of these operators. I'm not going to make the statement, explain their statements, and we're going to proceed with the physical setup and see what the statements might be. So, first of all, in geometric quantization, L2 functions on M are related to quantization of the cotangent bundle of M. So in other words, the Hilbert space of EFK is what you get if you take the Higgs bundle moduli space with real symplectic structure omega and quantize it via geometric quantization using the fact that it's a cotangent bundle. But if we're going to get anywhere in terms of predictions from duality, we need to understand this quantization via branes. So for this, the first step is to pick a complexification of the Higgs bundle moduli space that has some properties that I tried to explain, although I zoomed through it a bit fast. Well, the Higgs bundle moduli space is a complex manifold. Any complex manifold viewed as a real manifold has a canonical complexification, namely the product y1 times y2, where y1 and y2 are two copies of y, taken with opposite complex structures I and minus I. So I was the complex structure on y. We take I and minus I on the two factors. So then y hat has an involution that exchanges the two factors. It's anti-holomorphic because we took opposite complex structures on the two factors. And its fixed point set is the diagonal, which is a copy of y. So we've realized y as the fixed point set of an anti-holomorphic involution. And we can take the holomorphic symplectic form of y hat to be half omega on the first factor and half omega bar on the second factor. Then the restriction of this omega hat to the diagonal is real omega. In other words, y is Lagrangian for m omega, the diagonal is Lagrangian for m omega. This should be m omega hat, and symplectic for real omega hat. So this is the situation in which quantization of y using a Lagrangian brane supported on y, where y is interpreted now as the diagonal in y hat, makes sense. Moreover, the real polarization that leads to the Hilbert space studied by Edinger, Frankel, and Kazhdan does have the right properties that enabled Gaiotto and me to compare geometric quantization to quantization by branes. So therefore, the Hilbert space they used can be studied in brane quantization. I didn't want to just tell you that that step is important. Otherwise, we can study branes and gauge theory all we want. But how do we know it was related to the quantization that was assumed by Edinger, Frankel, and Kazhdan? Now, what are the observables in brane quantization? Well, here we should remember Hitchin's integrable system. The Higgs bundle moduli space has a Hitchin fibration over a complex manifold that's just Cn for some n. for linear functions on the base are Hitchin's commuting Hamiltonian. And classically, the global holomorphic functions are the pullbacks of functions on B. In other words, the algebra A naught of holomorphic functions on the Higgs bundle moduli space is the algebra of polynomial functions of the Hitchin Hamiltonians. Well, what are quantum observables? Well, for brane quantization, we have to define this funny quasitropic brane on y hat. It's just a product of quasitropic branes on the two factors, since y hat was a product, except with opposite complex structures and different symplectic structures. So you find that the algebra that will act on quantization of y is just A tensor A bar, where A was Ham on one side, A bar is Ham on the other side. And these are just quantum deformed versions of the algebras of Hitchin's commuting Hamiltonians and their complex conjugates. But in this particular case, you can show that even after quantum deformation, the two rings still commute. That's due to Hitchin for SL2 and to Balanson and Drinfeld in general. And the quantum deformed objects are commuting differential operators that are quantizations of Hitchin's classical commuting Hamiltonians. There's also an explanation by gauge theory of the fact that the quantum deformed ring is commutative. It's similar to the explanation I gave at the beginning of the commutativity of the Hegge functors. Now we want to understand how these observables act on the Hilbert space of L2 functions on the moduli space of stable bundles. First of all, there's no mystery about the fact that the algebra does act. That's just the statement that holomorphic and anti-holomorphic differential operators on M of G can both act on functions of M of G. Since M of G is birational to a cotangent bundle, the algebras have an interpretation as differential operators on the base, so they can act on functions on the base. Holomorphic operators trivially commute with anti-holomorphic ones, and the algebras of holomorphic and anti-holomorphic operators are separately commutative. So A tensor A bar will have an action on functions on the base. It's a commutative algebra, so they can be simultaneously diagonalized. And then we can ask, what are the joint eigenvalues of Hitchin's Hamiltonians and their complex conjugates? To answer this question, we want to apply duality. Well, to apply duality in this situation, where the quasitropic brane is a product of two branes, naively, we need to understand the duals of the three branes involved. So these are quasitropic branes on the Hitchin moduli space and another copy of it, and B is supported on the diagonal. So B, the first one, is the brane associated to deformation quantization. And as I mentioned before, a reinterpretation of a result of Balanson and Drinfeld is that its dual is the structure sheaf of the variety of opers, a certain Lagrangian submanifold. And similarly, the dual of the other one is the structure sheaf of L opair bar, the Lagrangian submanifold that parametrizes flat bundles whose anti-holomorphic structure satisfies the opair condition. So I've zoomed through this pretty fast, but two of the branes here have duals that are essentially known by a reinterpretation of a result of Balanson and Drinfeld, which, as I told you, Guyot and I struggled a lot with at one point. What about the brane supported on the diagonal? Here, there's an old folding trick that shows we don't have to worry about doing anything. So we had two copies of Y, which really meant two copies of the four-dimensional gauge theory. And away from the boundary, well, in the bulk of the two manifold, they're completely independent. So you could think of it as two sheets. And then the boundary condition associated with the quasitropic brane doesn't make them interact. It's just separate boundary conditions for the two copies. But on the other boundary, we have this brane supported on the diagonal, which glues them together. So we have two sheets that are simply glued together over one boundary. If you unfold it, we just have a strip of twice the width with one quasitropic brane on one side and its cousin for opposite complex structure on the other side. And in the middle, the black line is where the fold used to be, but nothing's happening there because gluing two things together on the diagonal did nothing except saying that the fields on the left and on the right agree on the common boundary. So we just got a single theory on a strip of twice the width with two different Lagrangian branes on the two boundaries. So we dualize the two boundary conditions to get two conventional objects in the Fukaya category. So in this, with this dual moduli space viewed as a real symplectic manifold in one of its real symplectic structures, these guys are just ordinary real symplectic manifolds. And we now simply have two objects in the conventional Fukaya category. The unconventional quadratropic brane has gone away after the duality. Now we're in a world that people who do the Fukaya category will be familiar with. So the algebra A becomes home from this Lagrangian brane to itself. Sorry. I made an embarrassing error. Sorry. The dual is on the B model side. So these are not, okay, they were Lagrangian indeed. But remember, there's a lot of structure that I warned you about before because of all the complex structures. Here we're in the B model. So the structure sheaf of the variety of Operas is a coherent sheaf. So my statement, however, was true in a different world. We're now in a conventional mathematical world with two coherent sheaves in a complex manifold. And we're just looking at intersections between two coherent sheaves, or hom between two coherent sheaves. So one algebra is hom from one sheaf to itself. That's just the algebra of holomorphic functions on one complex Lagrangian submanifold. The other is the algebra of holomorphic functions on a different complex Lagrangian submanifold. So here are the two dual pictures. I erased the central line, which didn't do anything. So we had a strip with two unconventional A model boundary conditions. The dual is a B model with two conventional B model boundary conditions. So now the physical states, here in this description, the physical states are L2 functions on that moduli space of G bundles. But in this description, the physical states are hom between intersections between two coherent sheaves. So hom from one coherent sheaf to another. And that has a basis that lives just on the intersection points. So in this case, well, Edinger, Frankel, and Kazan conjectured, and in some cases proved, that these two Lagrangians have discrete intersections. And so the hom space just has a basis with one basis vector for every intersection point. And that's supposed to be the basis that diagonalizes the Hitchin Hamiltonians. So maybe I need to say what an O-pair is. The definition of an O-pair is a flat bundle that viewed holomorphically is a non-trivial extension. I'm defining it just for SL2. So for SL2, an O-pair is a flat SL2C bundle. If you forget it's holomorphic, if you forget that it's flat and just view it as a holomorphic bundle, it's an O-pair holomorphically if it fits into a non-trivial extension. And similarly, it's an O-pair anti-holomorphically if it's a non-trivial extension anti-holomorphically. The statement that's elementary but possibly unfamiliar is that these conditions can both be viewed as holomorphic conditions in the complex structure where you're studying flat bundles. And the complex structure comes simply because SL2C is a complex manifold, complex Lie group. So in this picture, we just have the intersection between two complex manifolds, one flat bundles that satisfy this condition, the other flat bundles that satisfy this condition. There's no algebraic structure in which those conditions are algebraic. If there were, there couldn't be infinitely many discrete intersection points, as is actually the situation. So, So, as I explained before, using the anti-holomorphic involution, this hom space has a Hermitian inner product that you expect to be positive. The dual space does also. And you can show that the intersection points have to be non-degenerate, as conjectured by Edinger, Frankel, and Kazan, and proved in some cases, in order for the inner product to be positive. So explicitly, well, I think I'm going into too much detail here for the time, but explicitly you can show that if the intersection points, let me explain this a little bit. So consider an intersection point. An intersection point is a flat bundle E that's an O pair both holomorphically and anti-holomorphically. Then the anti-holomorphic involution that's used to define the Hermitian structure will map a flat bundle E to the complex conjugate flat bundle E bar. And that will also be an O pair both holomorphically and anti-holomorphically, since complex conjugation will map the holomorphic structure of one to the anti-holomorphic structure of the other, and vice versa. If E isn't isomorphic to E bar, you can show they're both null vectors for the Hermitian form, which in that case isn't positive definite. But the duality predicts it should be positive. So we expect that, as in one of the conjectures of Eddington, Frankel, and Kazhdan, E is always isomorphic to E bar. The claim is that a flat bundle that's both an O pair and an anti-O pair, that's an O pair both holomorphically and anti-holomorphically, is actually real. I suspected that the structure was actually the split real form, but that wasn't clear from the physics point of view. The physics point of view gave some additional interesting predictions about these intersection points, which there isn't really time to explain now. So, assuming the duality is true and the Hermitian form is positive definite, the joint spectrum of A and A bar corresponds to real O pairs. Now let me recall two statements of Valentin and Drinfeld. An element X of the ring of Hitchens Hamiltonians has two interpretations, according to them. It's a holomorphic differential operator on the moduli space of bundles, and it corresponds to a holomorphic function on the variety of O pairs. The complex conjugate statement is that an element X prime of the complex conjugate ring is an anti-holomorphic differential operator and is a holomorphic function on the variety of anti-holomorphic O pairs. So an intersection point of the two Lagrangian submanifolds determines a pair of eigenvalues of the two differential operators, namely the values of the functions fx and fx prime corresponding to x and x prime at the point P. And this is the proposal for the joint spectrum of Hitchens quantized Hamiltonians. So Eddington, Frankel, and Kazhdan also introduced Hecke operators as operators on the Hilbert space H that arises in quantization of the Higgs bundle moduli space as a real symplectic manifold. So I already explained that line operators give functors on the category of boundary conditions or branes, and moreover, there are dual pairs of functors in the A and B model categories. The same line operators represent operators on the quantum Hilbert space. In fact, the reason, what I'm about to tell you is the reason physicists call them operators. So I've tried to explain it with the following picture. Previously, we took a line operator that runs parallel to the boundary, and we interpreted it by moving it up to the boundary as a functor on the category of branes. We could, however, take the same line operator and let it run from left to right. We have to say something about the endpoints where it ends on the boundary, but if we postpone that, this picture is going to give a quantum operator, an operator in physical states, simply because if you start in the input with a physical state, and you do your quantum field theory transition amplitude, the output at the top will be some other quantum state. So T will have determined some kind of linear transformation on the space of quantum states. The last picture, I'll kind of skip it because of the time, but the purpose of the last picture is to explain what kind of data are needed at the endpoints. And from this last picture, you can see that the corner represents a hum from one brane to another. So the argument that showed commutativity of the functors associated, the Hecke functors viewed as functors on boundary conditions, immediately shows that the corresponding operators viewed as operators on quantum states also commute. Because they live at different points in C, we can move them up and down past each other in this picture with no singularity. And as in the discussion of line operators as functors, well, I'll skip the last segment. The same argument shows that the Hecke operators commute with the quantized Hitchens Hamiltonians. Again, you can move Hitchens Hamiltonian up and down past the Hecke functor, because you can assume that they're localized at different points on the hidden Riemann surface C. That hasn't been done. The last question of this level of generality is, what are the predictions of the duality for the eigenvalues of the Hecke operators? Well, to answer this, we'll start on the G-dual side. We're going to find the eigenvalues of a Wilson operator, W of P, acting on the Helm space, and then the duality will predict that the eigenvalues of the Hecke operator on the automorphic side will be the same. Also, we'll find what kind of data is needed for the corners or the endpoints of Wilson operator on the boundary. Well, since I'm taking a little bit too much time, I'll try to go through this a little bit briefly. So first of all, we start with a G-dual bundle over E with some connection over the 4 manifold sigma times C, and also a representation R of the dual group. To that data, there's what mathematicians call an associated bundle. E is a G bundle, but there's an associated bundle E sub R in the representation R. It also comes with a connection. And then WR of gamma for a path gamma in sigma times C is defined as simply the holonomy of this connection along gamma. For the present application, we fix a point P in the Riemann surface C, 2 points A and B on the left and right boundaries of sigma, and a path that runs from A times P to B times P, this path. Then, if E sub R at A times P and E sub R at B times P are the fibers of E sub R at the left endpoint and the right endpoint, then parallel transport defines for each connection a linear transformation from one fiber to the other. Or to state it more symmetrically, it defines an element of the Helm space from one fiber to the dual of the other fiber, from one fiber tensor with the dual of the other fiber into C, where R prime is the dual representation to R. So classically, that's what we get from parallel transport. Now, a quantum operator will come from a complex valued function of connections, which we don't yet have. What we have so far is that for each connection, we defined a linear transformation from some vector space to C. To get an operator, we need to supply elements in the two vector spaces. And then this linear transformation applied to V tensor W will be a function of connections, and its quantization will be an operator that we can easily understand, as it turns out. To avoid unnecessary details, I'll specialize to the case that the dual group is SL2 and the representation R is the two-dimensional representation, in which case the dual representation is the same. So in this picture, the boundary condition on the right boundary was that the G-dual bundle E, restricted to the right boundary, is an anti-holomorphic ochre, which by definition means that there's a non-split exact sequence, where K bar is the anti-canonical bundle of C, and K bar to the 1/2 is the square root. So if we pick a vector V in the square root of the anti-canonical bundle, we get a vector J bar of V in this fiber over here. Similarly, on the left boundary, the boundary condition tells us that ER prime has a subbundle K to the 1/2. So if we pick a vector in K to the 1/2, now the square root of the canonical bundle, we get a vector J of W in the fiber. And once they're picked, we have a complex valued function of connections that we'll interpret as a quantum operator. It's just W applied to J bar of one vector tensored with J of the other vector. Now, interpreting this as an operator is trivial because in the B model, we can actually assume that the connection is pulled back from C up to a possible twist by an element of the center of the dual group, which for SL2C, this should be, is plus or minus 1. So up to sign, W hat is just the natural dual pairing between the two fibers, and therefore its value at a given real ochre is simply up to sign, which comes from the center of the group, the pairing in the two-dimensional representation of SL2 between the two vectors. So this is the answer of Edinger, Frankel, and Kazan for the eigenvalues of the Hecke functors. So the duality predicts that on the dual side, the definition of TFP as an operator, first of all, requires the same data we used. That's true as was shown by EF and K using an algebra geometric formula. And then the duality predicts that the eigenvalues of the resulting operator will be what we found on the dual side, namely this, for all possible real opers. Both signs do occur. That's related on the G side to the fact that minimal Hecke modification of an SO3 bundle acts non-trivially on the second C4 inference. So I'm sorry I couldn't probably resist the temptation to explain a little bit too much in 1 hour. But what I've tried to do is to at least sketch the gauge theory interpretation of geometric Langlands and then to tell you how the analytic version of the theory fits into this frame. Thank you.
Okay, intriguing lecture. So once again, apologies to the people joining us online. We don't have capacity to take questions from you. Was there anybody in the room who would like to ask a question?
Say, why do you have to generalize the Fukaya category by including co-isotropic things?
Well, the original argument, the original example of complicit Orlov was to take two generic product of two generic elliptic curves. Then for special complex structures, there are holomorphic objects that don't exist generically. For example, the diagonal, if they're the same one, we're generally complex multiplication. But when they happen to have complex multiplication, there are more holomorphic objects. Then they had a particular, in this case, because the elliptic product of two elliptic curves is flat, they could be completely explicit about the duality between the B model and the A model. And the exceptional complex objects, their duals were not Lagrangian branes, they were coisotropic branes. And then they went on to show that the coisotropic branes they were getting have quite fascinating properties. I would say most of which are still a little understood today. Whatever is understood about coisotropic branes is quite fascinating.
Anybody else? Well, let's thank Edward again. Well, just a few short minutes before we have our fireside.